let us start today's discussion. We'll Today we'll try to understand the analysis of cables. Okay. So till now, see, we have discussed about arches and then portal frames, and you see in case of three-hinged arch, you have seen how to find out the bending moment diagram for a three-hinged arch. Basically, that is a determinate structure. Now, in case of cables, if you remember earlier, I have told you that in case of a cable structure will be always under tension. Okay, so there will not be as such any bending moment coming into a cable structure. So what is a cable structure, or where do we use it? That you need to first understand. So you see, cables basically, if you notice that there are suspension bridges. Okay, so in the suspension bridge, if you see, in that suspension bridge basically is a very important structural component. Okay, so basically in case of a suspension bridge, the cables are used. Okay, so what is a suspension bridge? So you see, suspension bridge, just I'll go little down now and then I'll explain the suspension bridge, then I will come up. So you see, this kind of bridge is called a suspension bridge. You see, this kind of bridge is called a suspension bridge, where you see this bridge deck, whatever is this bridge deck, if you observe, see, this bridge deck is not supported on these pillars. This bridge deck is not supported on these.
So voice clear नहीं आ रहा है sir.
Now is it clear?
Yes sir.
See, this bridge deck, whatever you are seeing, this deck is not supported on these two pillars, if you observe. Okay, how this bridge deck is supported? Who is actually taking the load of this bridge deck? See, this bridge deck is basically hanging from this cable. If you observe, this is the cable. Okay, and this is actually called main cable, and you see this main cable is passing over these piers. So these are the supports, these are the supporting towers. Through the top of these towers, this main cable is passing, and a part of this cable, it is going down, which is called basically the anchor cable, and it is anchored somewhere on the ground. Okay, now you see these cables, to these cables there are vertical members attached, and these vertical members are called hangers. Okay, so these hangers actually transmits the load of this bridge deck to this cable, and ultimately this cable takes up the load of this bridge deck through the tension capacity of the cable. So is it clear? So this is how a suspension bridge works. So in case of a suspension bridge, if you observe, the cable is one of the most important component. Okay, because you see the complete load is being carried by the cable only. Okay, so this cable, how to analyze this cable, that will be the part of our discussion in this class, and maybe in the next class also. Okay, so let us try to see few more things about the cable. So you see, that is why we are saying that in suspension bridges, cables form an important structural component. So you understand why cable is an important structural component? Because the load of the bridge deck will be transferred through the hangers to the cables, and cables will be ultimately taking the load using the tension capacity of it. Okay, Then next you see a suspension bridge, as I have explained to you, it will be consisting of two cables. You see, on one side of the bridge deck there will be one cable, and on the other side of the bridge deck will be another cable. So in a roadway, in a particular roadway, in a bridge, the deck will be supported with two cables and four pillars ideally. Okay, so the four pillar structure will be there, two on one side of the bridge, two on the other side of the bridge. Okay, and on the one side of the bridge there will be one cable, on just on the opposite side of the bridge there will be another cable. So the cables, as you have seen from the diagram, the cables will pass over the supporting towers. The cable will pass over the supporting towers, as you have seen. The supporting towers are these one, the supporting towers are these one, this one and this one, and you see the cable, this is your main cable, and you see this cable is getting passed over these supporting towers. Okay, so after you observe that the cables are anchored by backstage to a firm foundation. So basically you see, whatever is your main cable, this main cable, if you observe, this main cable is passing over the towers, and then you say there is a anchor cable coming. So this is a continuous kind of cable. This cable is being anchored at a particular with a proper foundation. Okay, because this anchorage will be ultimately this tension will be getting transferred through this anchorage to the foundation level. Okay, so this is what is actually the structural mechanics of cable. Okay, the cables are anchored by backstage to a firm foundation, you have observed, and the load of the deck is transmitted to the cables through closely spaced hangers, as I have explained you. So how the load will be getting transferred? So this is your roadway, and you see the vehicles will be running over this roadway. So when the load will come on this roadway, as well as the dead load of the roadway, that will be getting transferred through these closely spaced hangers. Okay, and these hangers will be getting attached to this cable. So ideally what is happening, the bridge deck will be passing the load to this hanger, and then this hanger will be passing this load to the cables. So finally, if you observe, the load from the deck will be transferred to the cables through the closely spaced hangers. Okay, now you see, this is called basically the dip of the cable. So basically, what is dip of the cable? Dip of the cable, if you observe, so this cable profile, what will be the profile of the cable, we'll discuss later. But if you see, if it is a cable like this, then from the top point of the towers to the bottom point of the cable, okay, the depth will be called as the dip of the cable. Okay, now if we go further, then you see, you must understand what will be the mechanism of the point over here and here. That means this cable will be passing through this support, and how the cable will be passing through this support, and how the load will be getting transferred from the cable to this anchor cable, that you need to understand. So the support mechanism over here you need to understand very clearly for a cable. Then we will go to the detailed analysis of the cable structure. And if you see, whenever we are talking about this cable, as you know, that cable is basically a tension structure. So the complete load, whatever will be getting transferred through the hangers to this cable, will be taken up by this cable through its tension capability only. There will not be any bending, there will be not be any other thing, there will not be any shear, nothing else. Okay, only tension, only and only tension will come in the cable. Okay, now you see, let us try to understand the mechanism of the support or the suspension tower. So the main cable, actually you see, it will pass over the suspension tower over, either it will be a frictionless pulley, it is a frictionless pulley, or it can be over a saddle support on rollers. We'll see what is a saddle support on rollers. Okay, but you understand what is a frictionless pulley. Okay, so pulley, you see, pulley is nothing but, if you have observed in the well, normal well, whatever we have in our house, some cases, you see, for pulling up the water from bottom of the well, we use the pulley. It is exactly the same mechanism. It is exactly the same mechanism as you will see over here. So you see, over a frictionless pulley. So this support mechanism at the tower may be of two types. One is over a frictionless pulley, or it may be over a saddle support on roller. So what is a saddle? You see, this kind of a blocked arrangement on top of the rollers placed is called saddle. Okay, and on top of this, on top of the saddle, the cable will be coming and cable will be passing on through this saddle, and then it will be going down, and then it will be anchored somewhere here. Okay, so you see, first let us try to understand the mechanism of frictionless pulley. So in case of frictionless pulley, if you observe, this is your main cable. So basically if you see, go a little bit top, and you see, this is the point where we are seeing the mechanism at the bottom. And you see, this is your main cable, so main cable will be coming under tension, so there will be a tensile force coming over here, and so there will be tensile force will be getting transferred through this pulley, over this pulley, to this anchor cable. Okay, so in case of a frictionless pulley, when you will be using a frictionless pulley over here, then, or you are using a frictionless pulley over here, then you see your transfer mechanism will be something looking like, it will be structurally, it will be something like this. So what does it mean? It means that main cable, when the tension in the main cable is T1, then this T1 will be ultimately getting passed over through this pulley, to this anchor cable, and let's say the tension in the anchor cable is T2. But you see, for equilibrium condition in such case, what you will have to have, this tension in the main cable, that is T1, must be equal to T2. Okay, so this is the first thing you should understand. So if the support mechanism is a or I'll not say support mechanism, the cable, where the cable will be passing over the suspension tower, if that mechanism through which the cable is passing is a frictionless pulley, then you see the tension in the main cable T1 will be exactly equal to the tension in the anchor cable, that is T2. Okay, now next is, you see, if you go to the saddle support or saddle on rollers, then you see there will be little change in the mechanism. Okay, so when you are talking about a saddle supported on rollers, you see, this is your main cable, and this is your anchor cable. So you see, if the main cable is having a tension T1, then your anchor cable will be having a tension T2, and in case of a saddle support, this T1 will not be equal to T2. Instead, what will happen? This H1, that is the horizontal component of this tension force will be equal to the horizontal component of this tension force. Okay, so basically the mechanism of saddle, because you see this roller cannot go down and it cannot come over to here. So this saddle, actually what is happening, this will move on this side or this will move little on this side. So to balance this saddle in position, to have a equilibrium condition, there must be horizontal force equilibrium. That means there must be H2 should be equal to your H1. Otherwise what will happen, this saddle will move over and over this roller, and it will just fall down of this support. Okay, so it cannot happen like that. So in case of the saddle support on roller, saddle supported on roller, the horizontal component of the tensile forces on both sides of the saddle, one will be coming from the main cable and other one will be coming from the anchor cable. That must balance. If it does not balance, then the saddle supported on roller will not be under equilibrium. Okay, so if that is the condition, if that condition needs to be there, then you see, if there is H1 is equal to H2, and obviously you see this T1 may be or may not be equal to T2, because this theta, the angle theta, or this angle theta, or you can say this is theta 1, which the main cable is making with the horizontal, that may not be exactly equal to the anchor cable, which is making an angle theta 2 with the horizontal. See, there is a possibility that theta 1 will become equal to theta 2. It all depends on your anchoring mechanism, and it all depends on your cable suspension. However, you see, if this theta 1 becomes equal to this theta 2, then you see this T1 will also become equal to T2. Otherwise, you see, if this theta 1 and this theta 2 are not equal, that means if the horizontal angle made by the main cable and the horizontal angle made by the anchor cable over when it is passing over a saddle, if they are not equal, then these two tension forces, that is T1 and T2, obviously will not be equal. Okay, however, the horizontal component of the tension forces needs to be equal, otherwise the saddle will not be under equilibrium. So considering that condition, this is very important condition, considering that condition, when the cable will be passing over a saddle supported on roller, in that case H1 will be equal to H2, and thus you can see from this diagram that if I take a cos component of T1, that is T1 cos theta, which is nothing but H1, should be equal to T2 cos theta 2. Okay, so T1 cos theta 1 will be equal to T2 cos theta 2. So what is H1? H1 is nothing but the horizontal component of this T1. So if this angle is theta 1, this is T1 cos theta 1, and on this side if you see the tension is T2, so if this horizontal angle is theta 2, so H2 will be equal to T2 cos theta 2. Is it clear? Is there any doubt up to this point? Okay, so let me proceed further. So now you see, after understanding this mechanism of this pulley, let us say I have just written it in words. So you see, in case of frictionless pulley, the maximum tension Tmax, so whatever is the maximum tension coming in the cable, that means Tmax, whatever is coming in the main cable, basically should be equal to the maximum tension Tmax in the anchor cable. So that's what we have understood just little bit earlier, that T1 should be equal to T2 should be equal to Tmax. Okay, Now in case of a cable passing over a saddle on rollers, what will happen? The horizontal component of cable tension is same in main cable and anchor cable. This needs to happen, otherwise the saddle will not be under equilibrium, as I have explained. Okay, so H1 should be equal to H2, and in that case your T1 may not be equal to T2. So in most of the cases T1 will not be equal to T2, but your H1 must be equal to H2. Okay, now the load from the deck of the bridge is transmitted through the hangers to the cable. You have understood how the load is being transmitted from the deck of the bridge to the cable. Okay, so it is transmitting, the load is coming on the bridge deck and the hangers are taking the load, and then those hangers are transmitting the load to the bridge deck. Now if we try to understand what will be the profile of the cable, okay, so you see that you'll be understanding from these two lines, these 2 points next we are discussing. See, if the number of hangers is large, so if you see there are many number of hangers, and the hangers are very very closely spaced. Okay, so what will happen in such case? So if the number of hangers is large, so what will happen? The load transmitted to the cables can be approximated to a uniformly distributed load. Why? See, very very closely spaced hangers, so you can see that very small length of deck, and that deck weight will be transmitted through the hangers to the cable. So you can assume, you can approximate, if there is closely spaced hanger, it will be just like a UDL, whatever you think, whatever you see in case of a beam or in case of an arch. So due to this above condition, when the hangers are very very closely spaced, in such case what will happen? The cable will assume a shape of parabola, because you see, if the UDL is coming and if there is no bending moment, as the cable cannot take any bending moment, it will be only taking up all the forces coming from the bridge deck through the hangers using the mechanism of tension. Then the shape the cable needs to assume must be a parabola, because you see, in case of a simple supported beam, if you put UDL over it, the diagram of the bending moment is parabola. So if the cable needs to support the UDL only using the mechanism of tension, the shape of the cable needs to be like parabola. And how it is taking the shape of the parabola? Because the hangers are closely spaced and the hangers are transmitting the load from the bridge deck to the cable, and because of the closely spaced hangers, it can be approximated as UDL. Is it clear? So due to the above assumption, you can see always in such cases, if you see the suspension bridges, if you generally see the suspension bridges, you will see the shape of the cable will be always like your always like your parabola. Okay, now you see next part, let us discuss. So how to analyze now this cable, how to find out the tension in the cable, how to find out the reactions forces on the support, how to find out how much tension will come on the cable, how much will be vertical reaction, horizontal reaction. Okay, so this part, the next part, we will be discussing about those things. Okay, so let us see. So is there any doubt up to this point, whatever I have discussed? See, philosophically, if you have you understood what is actually a cable and how the load will be transmitted to cable, how the support will be taking loads. So everything is clear. If you haven't understood, please tell me. Is it clear? Any doubt? Anyone? No doubt. So if I ask you how much will be the shear force in the cable, tell me. Anyone? What will be the shear force in the cable? Anuj? Hello? Anuj? Anuj, what will be the shear force in the cable? Bolo? Tell. No answer. Anuj. Ayon, can you tell what will be the shear force in the cable? Hello. Ayon Chakraborty, 84 roll number.
Yes, sir.
Can you tell what will be the shear force in the cable? Will there be any shear
Sir,
force coming?
vertical component of the cable.
Shear, will it be coming in the cable? See, cable structure is completely under tension. That is what I am telling, that if you are not understanding physically or philosophically, then you ask me. See what is happening. I don't know whether you are listening to these lectures or not, because so blank you are going. Multiple times I am asking one and no one is responding. So whether you are sitting in front of the phone or your laptop, I don't know, while the lecture is going on. See, Prama Niyogi is there. Prama Niyogi.
Yes, sir.
You tell me. See, don't switch off immediately your speaker. Okay, Prama. You switch on your speaker. Remain on. Why are you switching switching it off? Just answer to my question. Okay, first. See, my question is, how much will be the shear force coming in the cable and how much will be the bending moment coming in the cable? Will there be any shear force? Will there be any bending moment coming in the cable? Yes or no?
No, sir.
It will not come, right? Which force will be only coming in a cable structure? Can you tell?
The tension force.
Yes, only tension force. That is what I am trying to tell you. Okay. So please, you can now switch off your speaker. Okay. So you see, if you are not understanding things, then you should tell. Otherwise, see, these things will not be again discussed. We are going very slow, very slow. So if you are not understanding, then you should tell me. Okay. See, now let us go to the analysis of the cable. So you see, while analyzing the cable, if you observe, you see, this is the cable structure, and these are the two supports. See, the analysis of cable actually is very simple to do, because you see, cables, the shape of this cable structure is parabolic. Okay, so now you see, in this case, the supports are at the same level. Okay, so that means if the supports are at the same level, then the analysis of cable structure becomes more easier, because you see, whenever there will be support at the same level, there will be vertical reaction and there will be horizontal reaction at this support. Okay, so now you see, on the top of the cable, as you have observed, that through the bridge deck girder, from the bridge deck girder through the hangers, the load will be ideally transmitted to the cable, and the load finally will be a uniformly distributed load, whatever you are seeing over here. So let's say there is a uniformly distributed load W over the length of a cable, over the span of a cable. Okay, so this is the cable, and the shape of this cable, will determine what will be the shape of this cable. Okay, now you see, it's very simple to find out the support reaction. You see, what will be your VA and what will be your VB? See, totally it is W. So the total load, whatever is coming on this cable, on this support, is W into L by 2. So on both sides there will be WL by 2. How will you be able to find out it? You take just moment about B. So if you take moment about B, then you see, this VA into L, this will be VA into L, and then this is your W. So W into L W into L into L by 2. Okay, so WL by 2 into L by 2. So WL by 2 is equal to 0. So your VA is going to be equal to WL by 2. So what will be your VB? VB is also going to be equal to WL by 2, or you can say that half of the WL will be going over half. Total it is WL, so half of the WL will be going over here, half of the WL will be going over here. So the vertical reactions, when the support are at the same level, it will be WL by 2 and WL by 2. Okay, now you see, what will be the horizontal reaction? So what will be the horizontal reaction? See, just now we have discussed that horizontal reaction, be it a frictionless pulley, or be it a saddle on top of a roller, whatever it may be the case, you see, the horizontal reaction, that is H1, H2, or HA, HB, whatever you say. Okay, the horizontal component of the tensile forces will be equal. So that means at the support, the horizontal reaction components will be equal. So H should be equal to HA, should be equal to HB, as the tension in the cable is the only force. That is very important. So if there is any other than tension force, if there is any other force, then this condition will not prevail. As only the tension is the only force coming in the cable or in the main cable, so the horizontal reactions must be equal. Okay, so if the horizontal reactions must be equal, so using this condition, let us say, if I take moment about the point C, so if I take the moment about point C, so you see, at every point, if I take moment, at every point of this cable, if I take the moment, and as you have already understood, the cable structure is always under tension. So if I take moment about this point C, the moment MC, that is summation of all the moments about point C should be equal to 0, because you see cable structure is completely, always will be completely under tension. There will not be any bending moment coming into the structure. So this condition is very important. Okay, so at any point in a cable structure, if you take moment, sum of all the all the moments of all the forces about that point, that will be going to be equal to 0. So in this case your MC is equal to, if I take the summation of all the moments about C, that is actually the deep of the cable, that means the deepest point of the cable. As you have seen, this YC, whatever we are mentioning over here, that is actually the deep of the cable, as I have explained you earlier. Okay, so you see this MC, if taking this condition MC, summation of all the four moments of about C is equal to 0, you see what are the forces you are getting? You are getting this VA, you are getting this HA, and you are getting this W. Okay, so if you take moment about point C, you see what you are going to get. You are going to get VA into L by 2, and what is your VA? VA is nothing but your W L by 2 into L by 2, and then you see there will be horizontal force coming over here. So this is your HA. So this HA is going to create moment about this, which is nothing but this HA multiplied by this lever arm, and this lever arm is nothing but your YC. So this HA multiplied by your YC will come, HA multiplied by YC will come, and you see the length of the cable, that is W into L by 2. See, from here to here the length is L, so half of the cable, C is the middle point of the cable, so you see it is from here to here the distance is L by 2, so it is W into L by 2 into, if I take the moment about C, then it will be half of L by 2 again, so it will be L by 4. So you see that's what is written, W into L by 2 is the load, and what is the arm of the lever arm of this? That is basically L by 4. So W into L by 2, it will be acting middle of this L by 2 length, so that is L by 4, so L by 4 will be multiplied. Okay, so W into L by 2 into L by 4. So if you simplify it, then you see VA, we have put the value WL by 2 into L by 2 minus HA into YC minus WL square by 8 equal to 0. And if you see, what is this WL square by 8? This WL square by 8 is nothing but, if you observe, it is nothing but the what is called, it is nothing but the bending moment of a simple supported beam under UDL. Okay, so you see this WL square by 4 minus WL square by 8, that is going to give you HA into YC. If you simplify it, then WL square by 2 minus WL square by 8, which is going to give you WL square by 8. So HA into YC will have a value of WL square by 8. That means you see this is what actually is giving you why the cable profile is parabolic. Okay, so you see this is actually simple supported bending moment at a maximum point, whereas maximum simple supported bending moment for a simple supported beam under UDL. Okay, so you see this HA into YC, if you get, then how much will be the value of HA? So HA is going to be equal to WL squared divided by 8 YC. Okay, now what is this YC? You see YC is nothing but the deep of the cable. It's very important to understand. Okay, so you see, if you know the deep of this cable, if you know this value of YC, then you can easily calculate the value of HA. Okay, so HA is basically WL squared by 8 YC. So at a distance, now if you see, if I want to find out something over here, so at a distance x, let's say at a distance x from the left hand support, I want to find out the moment over here. So how much will be the moment? Obviously this moment is going to be equal to 0, because you know that cable structure will be always under tension. So summation of all the moments at a particular point on a cable will be equal to 0. So if you take the moment about that point, so you see, if you are taking moment about that point, so at a distance x from the support A, the moment mx. So if you take mx and you make this mx to 0, then what you are going to get, we'll see. So what is the mx? Mx will be nothing but your exactly the same way as we have done it earlier. So it is nothing going to be, it is going to be Va into x. So the vertical reaction is going to create a moment about that point will be Va into x, and Va is nothing but your WL by 2 into x, and then there is HA. So HA value we have already calculated in terms of YC. So HA is nothing but WL squared by 8YC, and how much moment it is going to create. So basically you see, if I go little top, you see this is your distance, this is your x, and this is your y. So we are taking moment about this point, we are taking moment about this point. So how much moment it is going to create? Va into this distance x, then HA multiplied by this distance y, and then this is your W. So this is going to create W into x into x by 2. So basically W x squared by 2. Okay, so that way if I come down, you see that is what is written. So mx equal to Va into x minus HA into y. Y is the distance from the horizontal level to the cable point, and W minus Wx squared by 2. Okay, now you see, so the value of mx, thus the value of mx, if you simplify this equation, you see you are going to get the value of mx. So how you are simplifying? You take x common, so basically W by 2 x into L minus x minus, you see, WL squared 8YC into 8 into y. Okay, now if you think, if you see that cable is under tension, so you see at any point, if you take this moment at any point, wherever may be this point, so at any distance x from the left hand support or right hand support, if you take moment at a particular point in the cable, so the mx is going to be equal to always 0. So considering this mx equal to 0, we will just make this equation equal to 0. Now what from this, what we are getting, you see, so W into x by 2 into L minus x minus W L squared 8YC into y, exactly the same, this part I have written here, equal to 0. So if I simplify it, what will be the value of y? So y will be equal to W x by 2 L minus x into this 8YC will go on the other part, on the numerator. So it is 8YC by WL square. So 2 4s are 8. So if I cut it with 2, 2 4s are 8, and then W cancels, then you see what will happen. This y is going to be equal to 4YC. 4, this 4 is over here, so 4YC by L squared into x into L minus x. Now you see, this is basically, if you observe this equation, similar kind of equation we have got for a parabolic arch also. So basically you see, this is the equation of a parabola. Okay, so considering this, see, y is equal to 4ax square, this form of equation you are getting. Okay, so basically this is the equation of a parabola. So basically you are getting a second order parabola in this case. Okay, so thus you can always observe that whatever may be the case, when the load is transmitted from the bridge girder to the hangers to the cable, the profile of the cable will be always parabolic. Okay, and how it is becoming parabolic, it is being explained over here. Okay, so if you see there, this if you see that when we are talking about this parabola, just I have given a note at the bottom. You see the slope, see the shape of a cable under its own weight is not exactly a parabola. Okay, so if you take the weight of the cable itself, because the cable will also have its own weight, right? So the shape of the cable under its own weight will not be exactly a parabola, it will be kind of a catenary. However, you see in practice what will happen, the self weight of the cable will be much smaller than the superimposed load. What is the superimposed load? The load whatever is coming from your bridge deck to the cable, superimposed load. So the shape of the cable along with its self weight may be assumed as parabola. You understand? So the shape of the cable, you can just, for considering the shape of the cable, you can just neglect the weight of or the self weight of the cable. Or if you consider the self weight of the cable also, then also the shape of the cable can be approximated as parabola only. Is it clear? Now you see, we'll be ending the class now. So you see, we have now found out what is the value of VA and what is the value of HA. So how much will be the tension in the cable? You see, this kind of support mechanism it is happening, so there will be tension in the cable in this direction. This is T, and T can be calculated, thus T max, whatever is written, you see T max can be easily calculated using HA squared plus VA squared root over. So basically you use Pythagoras theorem, or you or whatever mechanism you do. So VA cos theta, HA cos theta, and then you squared it up and you are going to get it. Okay, so T max is going to be equal to root over of HA squared plus VA squared. So the maximum tension in the cable, you see, you can very easily calculate if you calculate the value of the horizontal reaction component and the vertical reaction component at a particular support. From that, if you do T, you can easily find out the value of T max, that is equal to root over of HA squared by plus VA squared. So this frictionless pulley and saddle support already we have discussed. Now another one point is there, how to find out the value of theta. We will discuss it in the next class, and then we'll solve another, then we'll take up one problem. Okay, so if I request all of you, please try to go through this lecture note, as well as there is a solved problem I have given. Okay, so you please go through that solved problem also. Okay, so let us stop today here. Okay, and let me take the attendance and then we will complete. Okay, just a minute. Everyone is here, 19 members, 20. Let me refresh and then take it. Okay, Google attendance collected. Okay, so let us stop today. Thank you.